On a serious note though, this tiny thing right here fits perfectly into your pocket, doesn't leave a bulge in your pants. What the fuck? A huge thanks to my Patreon supporters for making this episode possible. Fellow mathematicians, welcome back to another video. Rona-chan has hit me. No, it didn't, but I thought you might like another disgusting intro here on this channel. Today we are going to look at an equation that someone sent to me via my cursed math memes Twitter page. It's the logarithm to the 1. I hate decimal expansions. Who puts them in exponents? I don't understand, but never mind. Logarithm to the 1 power plus logarithm to the 3 power being equal to 1, where the logarithm is obviously yet again the natural log, just like we handle it always here on this channel, number theoretically. And we are going to solve it in an improvised session together, you and me, my boy Krill and your daddy here. And yeah, I hope you are going to enjoy this video. I suppose that I'm going to be able to solve it in an improvised session just because I already have a bunch of ideas that I'm going to employ when solving this equation. But before we get into the main video, I would like to thank today's sponsor, The Rich, for sponsoring a video here on this channel. And I'm quite excited to have them as a sponsor because this wallet right here is extremely durable and really does a good job keeping everything together nice and tight. Up until a few weeks ago I was still using my old synthetic leather wallet, but I got rid of it after receiving my Rich wallet. To be honest, this little thing changed my whole pocket situation. It really does a good job being very light and sleek. It fits perfectly into your pocket and really doesn't leave any weird bulge in your pants. Other than that, it looks really good. It has this industrial carbon fibered look and it's so highly durable. I think that's probably going to be the last wallet I'm ever going to have in my lifetime. What I find to be the most positive thing is that you can hold up to 12 cards in your Rich wallet and also a bunch of cash at the back side. You can get an extra option to get a money clip on the back side such that you can carry even more cash with you. Pure mathematicians need this. Other than this one, the Rich wallet is available in a bunch of colors, so it doesn't need to be this one right here. That's a limited version which is only available on the rich.com website, nowhere else, but you can get it in yellow, for example, or other titanium colors which look really, really good. And since the materials are so highly durable, you are going to get a lifetime warranty on your Rich wallet, which is crazy if you ask me. And if you are still not convinced that this right here is a crazy good product, then make sure to check out their over 30,000 5-star reviews that they have received all over the place, Amazon, on their website, etc., which is absolutely crazy. That's a lot of reviews. So if this feels like it's something for you, if you think this wallet could be something for you, then make sure to check out the link at the top of the description. With it, you're going to get 10% off your first Rich wallet, as well as worldwide free shipping, which is absolutely crazy. And the second best thing is that the URL includes Papa Flammy, which is pretty cool if you ask me. So try it out and support the channel this way. It won't hurt a thing, even if I throw it away. It's so durable. Now we are going to dive into the main video, my boys and girls. So, what was my initial thought for this problem? So the thing is, I don't like this decimal expansion up here. I seriously hate it. It could die in the corner. It would be good. We are going to rewrite it because 1.5 is nothing but 3/2. And thus you might notice that we can actually rewrite this problem rather nicely. Because if we have the logarithm to the 3rd power, okay, right here as a substitution, for example, then this was my initial thought, then we would have on the one hand, okay, let's rewrite. This is logarithm of x to the 3rd power. Okay, this is logarithm of x to the 3rd power to the 1/2 power. This is just this exponent being broken up plus the logarithm to the 3rd power of x being equal to 1. And now you might notice what I meant by substitution at the beginning. Let's say this thing right here, log of x to the 3rd power, is going to be some, I don't know, t. Let t be equal to the log to the 3rd power of x. Then our equation is going to transform into t to the 1/2 power, so square root of t, plus t being equal to 1. Okay, I thought this would turn out more nicely. I mean, I'm thinking right now, can we... The thing is, yeah, I was thinking we are going to turn up with a simple polynomial, but that's the square root of t. This is not nicely solvable. Oh yeah, if we were to substitute t to the 1/2 power, so let t to the 1/2 power be equal to, I don't know, let's get a cool variable. Let's say, I don't know, u. Oh, that's so relatable. Am I right? U is so relatable. Then this is going to turn into, okay, this is going to be u plus t is hence nothing but, okay, if we were to square this, then t is nothing but u squared plus 1. No, is equal to 1. Subtracting 1 on both sides is going to give us 0. This is good. That's just a quadratic polynomial, and this is really easy to solve, to find out the roots. So the roots are going to be u1 and 2, two solutions. They are going to be, okay, we are going to get -1 plus minus the square root of, this is going to give us 1. Minus and minus is positive, so plus 4 over 2. This is cool. This is Fibonacci. This is kind of Fibonacci. So this right here is the square root of 5. So on the one hand, we are going to get u1 is equal to -1 plus the square root of 5 over 2, and u2 is going to be -1 plus the square root of 5 over 2, which is really cool in itself, because this right here is negative, our boy the golden ratio. And this thing right here is, if we were to bring negative to the front, negative the conjugate of the golden ratio. Exactly. So we get the golden ratios out, which is cool in itself, if you ask me. Now the thing is, oh yeah, this is kind of good. Those are our roots in u. And now, what is u? Yes, u squared is equal to t, but this is also the logarithm to the third power of x. Meaning overall, if we were to square those two roots respectively, we are going to get two solutions to the logarithm to the third power out on the other side. Ooh. Okay. Yeah, let us just compute this. I was just thinking about something. Improvised session, that's the good thing about those. I can think a tiny little bit while doing everything. So at first let us square those roots. Then we are going to get that u1 squared is hence nothing but phi conjugate squared. But this is not a problem if we have those squared, because if you remember, for example, phi squared plus minus phi minus 1 is equal to 0. So the golden ratio and also its conjugate were the solutions to this polynomial x squared minus x minus 1. Meaning overall that, for example, phi squared is hence nothing but phi minus plus 1. And also phi conjugate squared is nothing but phi conjugate plus 1. Okay, phi is nothing but, so the golden ratio is 1 plus square root of 5 over 2. Adding 1 to this is 2 over 2, so this is going to give us 3 plus the square root of 5 over 2. And on the conjugate is going to give us 3 minus the square root of 5 over 2. Those are the ones. So we are going to get on the one hand 3 minus square root of 5 over 2. And on the other hand, for u2 squared, we are going to get 3 plus the square root of 5 over 2. Those are two solutions to the logarithm to the third power of x. And this is why I got a tiny little bit stuck, because the thing is, this equation right here, so if we were to solve for the logarithm to the third power of x, this equation is going to have three solutions, because that's basically, if we were to take base e on both sides, then I mean you can interpret it as a function of the third degree, and meaning it's going to have three real or complex solutions. But the thing is, if we have two solutions to u, then we are also going to get 3 more solutions out on the other side, meaning we are going to get 6 solutions out on the other side, but those are too much because this equation right here is going to have at most 3 solutions. No, exactly 3 solutions, I'm terribly sorry, but at most 3 real solutions, let's put it like this. So, meaning with those 2 and then 3 we are going to get 6 solutions out, which is kind of bad because we need to plug all the solutions into here and see if they are actually solutions to the original problem. That's going to be quite a mess, but we are going to find out what they are. We are going to try and find out. I think. Let us go through the process of solving this equation now. So log to the third power of x being equal to u squared. Now, if we were to take the third root on both sides. If we were to take the third root on both sides, I mean we are going to get 1 real solution each, obviously, which is the third root of conjugate squared and the third root of phi squared. But in a normal case, since this is a third degree one, we are also going to get roots of unity out on the other side. So for those of you who don't know what this is, we are going to take a step backwards and talk about roots of unity, because this is probably what is going to come into play here. Let us suppose that we have a complex number. I have just recently talked about complex numbers again. Complex number is r times e to the I phi. Phi is a bad variable here. Let's say theta, okay? Doesn't matter. Var theta. This right here is a theta, okay? This right here is a theta. Do not judge me. So this is our complex number. And let us suppose that we have, for example, a 1. Because if we were to take a look at phi squared, for example, phi squared is the same as 1 times phi squared. This is what we need to take into consideration, because if we take the third root, we need to take a look at the roots of unity of 1. Okay, so those are like the roots of unity. There's no other name for it. I can come up with another name right now. So what we are going to do is we are going to raise this right here to the 1/3 power, leaving us overall with z to the 1/3 power. Okay, this is like taking the third root, being equal to the third root of r times e to the I theta over 3. Okay, this is the first step that we are going to take. Now, what is going to happen is, if our log to the third power of x is just some, I don't know, let's say log of x is nothing but w, for example, so this right here is w to the third power. Then, if we were to plug this into here, then our solution for w, so our solution log of x, are going to be w to the third power to the 1/3 power. If we were to substitute our w to the third power for our z, it's going to be exactly w, our solutions. We are going to get 3 out on the other side. And this is going to be exactly our third root of r times e to the I theta over 3. And now we need to take a look at what our omega actually was. Our third root of omega is going to be exactly corresponding to this problem right here, because our omega to the third power in itself was nothing but, for example, our golden ratio squared. Meaning, if we were to take a look at what this is corresponding to as the golden ratio, then our radius that we are going to have is going to be the golden ratio, obviously. So this is like the length of the vector, because this right here was basically a real number, and we are going to reformulate it in complex terms. So meaning, for example, for the golden ratio part, we are going to get the golden ratio squared in here. And now this is the part where we had our 1 originally. Our 1, we are going to reformulate it such that we are going to get to 1 in the complex plane exactly 3 times. We are going to go to our 1 3 times. So basically the idea behind roots of unity is that we are going to start at 1 right here, then we are going to go around it. This was a rotation of 2 pi, and then we are going to go around it yet again. This was a rotation of 4 pi, and the original rotation, this is the real root that we are going to have, is going to be at 0 pi. Okay, so what we are going to have are 3 solutions in total. One solution corresponding to the cube root of phi squared times e to the I. Okay, first one is 0 pi over 3, so this right here is just going to give us 1 overall. And the second solution, or we are going to have as a solution, this is weird notation, but I hope you see where I'm getting at, is the third root of phi squared. Okay, next up is going to be e to the I. E to the I, next rotation is 2 pi over 3. Or we are going to have the solution, the third root of phi squared times e to the I 4 pi over 3. Now here's a thing that you can do. We know that we can rewrite this using exponentiation rules as e to the I pi to the 2/3 power. And e to the I pi, by Euler's formula, Euler's identity, is nothing but -1. This is what you are going to get. So this right here is -1 to the 2/3 power. And what are we going to get here? By the same arguments, we are going to get that this is nothing but -1 to the 4/3 power. Those are the 3 solutions. This one, this is the real root, and we're going to get 2 complex roots here overall. Those are the 3 solutions we can get for our case where we have phi squared as our complex number, you could say, for the roots of unity. And we can also have another case with our phi conjugate that we can plug into here. So overall, we are going to be left with 6 solutions, namely being, okay, we are going to have this one. And also we are going to have -1 to the 2/3 power, third root of phi squared. And then -1 to the 4/3 power, third root of phi squared. Next up is the third root of phi conjugate squared. Then -1 to the 2/3 power, third root of phi conjugate squared. And last but not least, -1 to the 4/3 power, third root of phi conjugate squared. Those are 6 solutions, and only 3 of those can fit with this equation right here. I'm not going to go through all 6 because this seems like a weird hassle, okay? This seems like a lot of hassle, but I'm going to try to find at least one solution out of all of these. Let us see if anything fits. Let us take a look at the real solutions, for example. Those should be easy to verify. Let us plug. So this right here, those are all the solutions we can possibly have for the log of x. Okay? They are all corresponding to our omega, which is the log of x. This is how we redefined it here. And now let us plug, for example, this real root into here and see if it corresponds to a solution. So we are going to get, if we have phi to the 2/3 power, this is what we have here, this is nothing but this, to the 3/2 power, okay, plus, and then we are going to get phi to the 2/3 to the 3rd power being equal to 1. This is the question if this is the case. So now those are going to cancel out. They are going to be to the 1st power, meaning this right here is phi plus phi squared being equal to 1. And this is not a solution because our original equation for Fibonacci was that phi squared minus phi minus 1 is equal to 0. So this right here does not correspond to a solution. Now how about this right here? Okay, let us take a look at this one. This is going to be the last one. We are going to try out, maybe it's a solution, let us see. Okay, we are going to get -1 to the 2/3 power times phi to the 2/3 power to the 3/2. And then we are going to get plus -1 to the 2/3 power, phi to the 2/3 power to the 3rd power being equal to 1. This is what we are going to test now. So those are all going to cancel out, leaving us overall with -1 to the 1st power. So this is -phi, this could be good. Then we are going to get this, and this is going to cancel out. -1 squared is +1, so we are going to get plus phi squared is equal to 1. And this is exactly cool because phi squared is equal to 1 plus phi. So this right here is indeed a solution. Then I do suppose, since this did not work out, and this right here, this phi conjugate is the solution to this polynomial 2, then this is probably also not a root, but this one right here is a root. And I can only guess, okay, don't take my word for it, this is just a wild guess. And then one of those two must be another root of this problem, but I leave this as an exercise to the reader, and I think this concludes the problem, and I hope I did okay. This became more of a mess than I thought it would. If you did enjoy this video, please like, subscribe, make a comment, channel if you like. You can find the whole improvised session playlist down there in the description. Also, don't forget to check out STEM merch and also the rich wallet, so many product placements, but honestly, this thing right here is pretty good. Does a good job. Really fits nicely into my pens, okay? Doesn't leave a bulge in my pen. But other than that, thank you guys for watching. If you enjoyed this video, please like and subscribe and comment channel if you like. Don't forget to go over to Flammy Maps too. I got a lot of content going on over there. Up until the next video, I'll show you guys a Flammy day. Ciao!